Newman projections represent ways that we can draw molecules that allow us to see interactions between atoms, groups of atoms, or bonds when they're nearby each other. Ethane is a simple molecule that allows us to learn how to draw Newman projections. That's what's on this page. On the upper left, you can see that the way that this is oriented, our hydrogens are staggered from the ones that are in the back. As we rotate the carbon-carbon bond, these hydrogens then are eclipsed. Now, if we visualize the carbon-carbon bond directly down the center, we get what's on the bottom right, and that is our Newman projection. When you're visualizing a Newman projection, it's important to know that this carbon that you're looking down the center of, which is here, represents two carbons, the one in the front and the one in the back. They're perfectly eclipsed from each other, which is why they don't offset each other. The green atoms are in front, you see these three hydrogens, and the magenta atoms are the ones in the back, or they're supposed to match the red ones in the back here. You'll also notice that the sigma bonds that are in the front meet at the center of our circle, whereas the sigma bonds in the back meet at the outside of the larger circle, and that's to help us with perspective. This conformation is called a staggered conformation, and in a staggered conformation we have angles between the atoms in the front and atoms in the back, or sigma bonds in the front or sigma bonds in the back, that are all identical, and that's this angle right here, and that's 60 degrees. This angle is called a dihedral angle, and when we take this central carbon-carbon bond and we rotate it, that dihedral angle changes. And so the remainder of this chapter is all about the energies of interactions between ethane and others as that dihedral angle changes. Let's practice by drawing the Newman projection for this organic molecule, which has a bromine and a chlorine in position 2. The first step in drawing a Newman projection is to determine which two carbons will make up the sigma bond that you're visualizing. In a 4-carbon molecule like this, most commonly we're talking about the carbon 2 and 3 right in the center of the molecule. For molecules that are a little bit more complex or larger, those two atoms will have to be specified. So for this one, we're going to be looking down the C2-C3 bond. We can do so either by visualizing it in this direction, or we can look at it in this direction. So let's first try drawing the Newman projection in the first way that I had shown, and I'll label that A. So our Newman projection will be here. We begin by first drawing the circle that represents carbon 2 in the front, and 3 is perfectly eclipsed behind it. The next step is to draw the 3 attachments to carbon 2 that we can see that are in the front of the molecule. We have the methyl group at position 1, the chlorine, and the bromine, and they are positioned as such. So the methyl group is pointing directly down, the bromine is up and to the right, and the chlorine is up and to the left. Despite the fact that we understand all of our carbons are tetrahedral in their geometry, you'll always draw these sigma bonds and atoms at 120 degrees to each other. Now let's consider the atoms attached to carbon 3. From our point of view, there's a methyl group that is straight up here. That's the carbon 4 that's labeled in the structure. And then there are 2 hydrogens. One of them is down and to the right, and one of them is down to the left. And you'll note that I'm maintaining that 120 degree angles between those groups. And in a perfectly staggered conformation as I have drawn, the dihedral angles between atoms or groups in the front and back are all 60 degrees. Let's go ahead and consider what that Newman projection would look like when visualizing from the other direction. Again, we begin by drawing a circle that represents carbon 3 and 2 is in the back. Next, we need to add the 3 attachments in the front. We have a methyl group here pointing straight up. We have a hydrogen down and to the left, and a hydrogen down and to the right. In the back of the molecule, our methyl group on position 1 is directly down. Then we have a bromine that is up and to the left, and a chlorine that's up and to the right.
Both of these Newman projections accurately represent the structure as I have it drawn in that conformation. Neither one is more right than the other. We're simply visualizing it in different directions. You've already seen for ethane that the most stable conformation is that where the carbon-carbon sigma bond is rotated so that the CH sigma bonds and the hydrogen atoms themselves are in a staggered conformation. Let's consider the conformational changes we're going to see as we rotate the carbon-carbon sigma bond. As the dihedral angle changes, those sigma bonds and the hydrogen atoms are either becoming staggered or eclipsed, and those represent changes in energies. In the staggered conformation, we have a relatively low energy. So if we were to plot energy as a function of bond rotation, and this axis represents that our staggered conformation that I'll mark with an S represents a relatively low energy. As we begin to rotate the carbon-carbon bond to achieve an eclipse conformation, you can see that the energy required for the rotation increases. So that's going to represent a higher energy. And as we continue to rotate, we go back down to a staggered conformation, and so our energy of rotation looks like this when plotted on a graph. Since I didn't address how to draw a Newman projection of an eclipse conformation, now would be a good time to do that. So let me rotate this a little bit more and begin as we did before by drawing a circle to represent the carbon bond that we're looking down. In the front, I'm going to draw 3 bonds here, which represent bonds to hydrogens. And then, if in a perfectly eclipsed conformation, in theory, the sigma bonds and hydrogens are exactly behind the ones in the front, so that's a little tough to draw. So instead, we offset them a little bit. Draw the hydrogens a little smaller, so we know that they're in the back. As I continue to rotate this back to the staggered conformation, we can look at the two and determine what the barrier of rotation is that gives rise to the higher energy that you saw in the graph below. In the eclipsed conformation, the hydrogen atoms are too small to have any sort of negative energy cost with regards to sterics. However, the sigma bonds are eclipsed, and those sigma bonds are filled with electrons, so there is a natural repulsive force in the eclipsed conformation that adds to our overall rotational barrier. In the staggered conformation, we have a favorable attraction between the filled sigma bond orbitals and the antibonding molecular orbitals that are behind them. And so between the two of these forces that we see, we have a combination effect, which we call torsional strain, that is 4 kilojoules per mole per interaction. And since there are 3 sets of sigma bonds that interact, that equals 12 kilojoules per mole of rotational strain energy. And that's the number that we see here in the graph. In propane, you might imagine that our rotational barrier is going to be a little bit more complicated by the addition of the extra carbon. So let's stop this in the staggered conformation. And let's draw another energy diagram, where this is energy, and then this line represents our rotation. Currently, we're in the staggered conformation, so I'll make that a low energy S. And then we'll start to continue our rotation over to an eclipsed. And there we are. At this point, not only do we have the torsional strain that we described for ethane, and that's no different, we have 3 sigma bonds aligning with each other, and that gives us 12 kilojoules per mole of strain energy. And we got that by understanding that we had 3 torsional values to add up. What's new now is that we have some steric strain, and that's the strain between the methyl group that's in the back interacting with the hydrogen in the front. And it's actually quite a small number, but that's 2 kilojoules per mole of energy. So if we add these together, we come up with 14 kilojoules per mole. So as this molecule continues to rotate, it goes from staggered to eclipsed conformation, back to staggered and eclipsed and so on. And as it does that each time, it's passing through an area of high energy. It requires 14 kilojoules per mole in order to rotate through. So that's this distance right here, 14, and the same distance here, 14, and we could go on through a full 360-degree rotation. Butane is the most complex example that we're going to look at here. As this molecule continues to rotate and eventually reaches a position where we can visualize the Newman projection, you'll see that it's in a completely staggered conformation. This is our lowest energy conformation, where there is no torsional strain and no steric strain. So I will mark S as our lowest staggered conformation energy here. Let's go ahead and start rotating this a little bit. I'm going to rotate the front of the molecule till it's in the eclipsed conformation, and then we'll stop here. Anytime we're in an eclipsed conformation such as this one, we're going to have torsional strain, and that's going to add up to 12 kilojoules per mole of energy because of the 3 sigma bonds that are aligning. You'll also remember from our prior example that we introduced a new strain called steric strain between a methyl group and a hydrogen. And we have 2 of those. There's a methyl group in the back of this molecule interacting with the hydrogen in the front. Here we have a methyl group in the front of the molecule, and behind it is a hydrogen. So we have 2 of those occurring. So for this example then, since each one of those is 2 kilojoules per mole, we're going to have a 4 kilojoule per mole steric interaction that we're going to need to add. And so altogether in this position, we have 16 kilojoules per mole of energy, strain energy. So I'll put that E in here for our eclipsed conformation, and I'm going to put 16 kilojoules per mole underneath it. Let's hit play so we can watch this molecule rotate again to a staggered conformation right there. So we'll get rid of our torsional strain and our methyl hydrogen steric interaction and reconsider the structure right now. We do have no torsional strain, but we also have a steric strain that's occurring between these 2 methyl groups. Now these are rather large groups. They are not eclipsing each other, but they're close, and so this carries a unique name known as a Gauss interaction. And a Gauss interaction specifically refers to a 60-degree dihedral angle between 2 large groups. So these 2 methyl groups are Gauss to each other. And because they're larger, there's a steric value that gets added. So we have this Gauss steric interaction, which costs 3.8 kilojoules per mole. So down in my energy diagram, our next value is going to be a little bit lower in energy, but higher than our initial staggered conformation. This gets a new name. I'm going to just call it G for Gauss, and I'll write 3.8 kilojoules per mole of energy here. The last conformation to consider, if we allow this to continue rotating around, will be here. Let me back up a little bit, where the 2 methyl groups are completely eclipsed with each other, and the sigma bonds are eclipsed as well. So we're going to get our torsional strain, which I'll abbreviate here, and that's 12 kilojoules per mole of energy. And because the methyl groups are eclipsed as well, we're going to get 2 different effects there. One of them is a steric effect because the 2 methyl groups are large and they're encroaching on each other's electronic space. But also, if we compare the standard angles that we expect to see in butane, this angle here is pretty close to a tetrahedral angle. But as that middle bond rotates into this position, which is the eclipsed position that you now see in that Newman projection, this angle has to bend and flex. In fact, it's actually going to appear more like this. So that angle goes from a tetrahedral angle to something that's pretty close to about 112 degrees, which really puts an immense amount of strain on this conformation. So that strain that we're going to add from the methyl-methyl interaction is going to cost us 7 kilojoules per mole of energy. And so total, we have 19 kilojoules per mole strain energy for this conformation. I'll use E again to designate an eclipsed interaction, but you'll definitely want to remember that there's two different sorts of eclipsed conformations here. So, as we begin rotating from the staggered conformation, we go through a 16 kilojoules per mole eclipsed value, down to a gauge conformation, and back up to a 19 kilojoule per mole eclipse conformation. And this goes back down to gauge and continues through the whole 360-degree rotation. Let's watch that one more time through a full 360-degree rotation. We start with our staggered conformation and begin rotating, and our energy goes up until we reached our first eclipse conformation. We begin going down to a gauge conformation, back up to a high energy eclipse conformation, down to a gauge, back up to a lower energy eclipsed, and down then to our starting staggered conformation.